Hey, welcome back. In this video, we're going to dig a little bit deeper on the graphs of logarithmic functions. Specifically, we're going to talk about increasing and decreasing logarithmic functions. Those are related to the conversation of whether they're the inverse of a growth exponential or a decay exponential. And then we're going to get a little bit into the transformations of log functions, specifically focus on the domain of log functions. And when we introduced logarithms, we introduced it through the idea of the inverse of the exponential, which is exactly the role of the logarithms. So let's quickly go through that again. Here we have the graph of y equals 2 to the x. Importantly for these exponentials of this form right here, we go through the points 0, 1. So if our exponent is 0, we output a 1. And through 1 comma the base. In this case, the base is 2. So the 2 points are 0, 1 and 1 comma 2. Well, now then, if we create the graph of the inverse of y equals 2 to the x, which is the log base 2. And you can see we're reflecting it over that line, always y equals x. We have the same points, but now we've changed the inputs and outputs. Importantly here, what we're graphing now is the log base 2 of x. And instead of going through 0, 1, it now goes through 1, 0. And instead of 1 comma 2, it goes through 2 comma 1. All right, just to dig a little bit deeper and to analyze these graphs a bit more, we have these points, again, 0, 1, and then 1 comma the base. Importantly here for exponentials, we have a domain of all real numbers, which we identified, meaning we can plug in whatever we want into this function without breaking any deep mathematical rules. Importantly, though, is we have a range that's strictly positive. So we have only positive outputs from these exponentials, and that's because of this horizontal asymptote at y equals 0. And then as previously stated, with the log base 2 of x, all we're doing is switching inputs and outputs. So we have the same points. We've just switched their x and y values. For the domain and range, those just flop also. So whatever was the domain of the original function is the range of the inverse and vice versa. Specifically, that means the domain of the log function is the range of the original. So this is strictly positive numbers. And the range is all real numbers. And you can see based on the graph, both of those, specifically this horizontal asymptote at y equals 0, that was the restriction of the outputs of the exponential function, now becomes a restriction for the domain, meaning this horizontal asymptote becomes a vertical asymptote at x equals 0. And again, this is a review of what we've talked about before when introducing logarithms. But in this case that we're using again here, this is a growth exponential and its related inverse. Importantly, both of these functions are increasing. As you increase the input, the outputs increase. Let's now take exactly the same conversation, but look at a decay model. All right, so in this case, we're looking at y equals 1/2 to the x. This is exponential decay because our base value is between 0 and 1. And as we look at this right here, importantly, we still go through these 2 points, 0, 1, and 1 comma the base right here. The difference is that base of 1/2 is what creates this decreasing model, this decay. And so then if we take this, again, with exactly the same setup, the same domain, same range, it just behaves differently. Again, we've talked about this, the idea of this is a more of a vertical flip. You could rewrite this as 2 to the negative 1. This would be 2 to the negative x. But we don't need to worry about those details. Just knowing the fact that this is a base between 0 and 1, it's this decreasing decay model. And then now if we reflect this over the line y equals x, so then here we have the graph of y equals the log of 1/2 of x, the base of 1/2. And importantly, this function is also a decreasing function, just like our exponential right here. Though it looks significantly different, it actually has all the same attributes as our other log function. It goes to the point 1 comma 0, which is the reflection of this, and 1/2 comma 1. The interesting part here is that when you flip this point 1/2, 1, you'll see that that comes before that x-intercept now. And our function is now coming from positive infinity from that vertical asymptote there, going through the point 1/2, 1, and then 1, 0. Importantly, this is a decreasing logarithmic function. It has all the same attributes, but because of how the attributes switch from the exponential growth to decay, the logarithmic functions will act the same. And importantly here, we still have this vertical asymptote at x equals 0, but we're decreasing through this domain of this function, again, through the point 1/2, 1, and then 1, 0. So the real purpose of just giving this example isn't to say that anything's different and you have a set of rules. Actually, it's all exactly the same. We're just taking our exponential points and flipping them with exactly the same setup. The difference is that if your base is this base between 0 and 1, you'll have a significantly different looking graph, and you'll have a decreasing logarithmic function instead of an increasing logarithmic function. All right, that just gives us a little review of the basics of logarithmic graphs, specifically the increasing and decreasing versions of the logarithmic graphs. Let's now do 2 examples when applying transformations to log functions. All right, in this example, we're being asked to sketch a graph of f of x is the log base 3 of 4x plus 3. So 2 things are going on here. First, I'm going to identify the transformations that are acting on right here. I'm going to need to factor out this factor of 4 for this inner function. We always got to factor before we apply our transformations. And then I need to remind myself all about the log base 3, which will be the toolkit or the base function for these transformations. So first and foremost, what I'm going to do is divide out this 4. I always need to factor these inner functions right here, or these inner transformations, in order to apply the methods in the same order. There are methods to do it without factoring, but if we use our same strategy of always doing our stretches and flips first and then our shifts, we always need to factor this out. And so what I'm first going to do is factor a 4 out of both of these terms, which again, if this always feels weird, it's equivalent to dividing. You put a multiplication of 4 on the outside and you divide each of those terms by 4. I'm sure you all feel fairly comfortable with that. But this will give me an x plus 3/4. And when you do this, you can always check, distribute this 4 through and make sure that this expression is exactly the same as that one. But importantly for our conversation, this multiplication by 4, now inside of our function, is a compression horizontally by 1/4. So it's always that factor of 1 over that factor right there. And this plus 3/4 right here will denote a shift left 3/4 units. All right, so the next thing that I'm going to do before I apply these transformations is just remind myself about this base function, which is the log base 3. And so for the log base 3, I know it goes to the point of 1, 0, because every logarithm without transformations goes through that. Again, what I'm graphing here right now is the log base 3 of x, just to give me some foundation for this transformed function right here. So I go through this point 1, 0, and then I also go through the point 3, 1. And this function, before it's transformed, will look like this. And importantly also has this vertical asymptote that runs right here at x equals 0. And when you do this, you absolutely don't have to graph this base function, but it always helps me not make mistakes when I start with my points. I'm going to use these 3 things, the vertical asymptote and these 2 points, as a basis for these transformations. All right, as stated a second ago, what I'm going to do is take those 3 points and I'm going to run them through these transformations right here. I always do my stretches or compressions first. So what I'm going to do is compress horizontally by 1/4. What that means is I'm going to multiply the x values by 1/4. This also affects the vertical asymptote, but beautifully, since it's 0, multiplying by 1/4 is not going to do much. And so this is a horizontal compression by 1/4, and that means multiplying the x values by 1/4, so I get 1/4, 0 and 3/4, 1 as my new points. Then what I'm going to do is use my horizontal shift here, so I'm shifting left 3/4 units. That means I'm going to subtract 3/4 from both of my x values here, and so this is left 3/4 units. And when I subtract 3/4 from both of these, again to the x values, so this right here is, so 1/4 minus 3/4 would give me a negative 1/2, comma 0, and then 3/4 minus 3/4, well that's easy, that's 0, comma 1. And importantly right here, this horizontal asymptote was the same in this compression because it was, again, multiplying that by 1/4 does nothing. But importantly, I'm shifting less 3/4 units in this case. So now my vertical asymptote is at x equals negative 3/4. Now I have all the information I need to sketch a pretty dang accurate graph of this log function right here. So these, after these two transformations, I have the points negative 1/2, comma 0, which would be right here. I also have the point 0, comma 1, which gives me this point right here. So this point right here is the negative 1/2, comma 0. This point right here is 0, comma 1. And then all I need to do now is add my vertical asymptote, which is now at negative 3/4, which is right about, let's say, right there. So that asymptote got shifted left, negative 3/4. And now that I have that, we knowing again what we did was compress this and shift it. And this looks pretty good. All I need to do is kind of provide a nice sketch of what this looks like now. And so this is a graph of f of x equals the log of 3, 4x plus 3. Again, last thing to emphasize, when I'm looking at a transform logged function, what I'm first going to do is identify these three components. 1, comma 0 and the vertical asymptote at x equals 0 will always be these fundamental pieces of a log function. The change is, when my base change is this value right here. So since I have a base of 3, this is 3, comma 1. Beautifully, if this was a decay model with a base between 0 and 1, it's exactly the same. It looks different when I graph all the information together. But I take those 3 points, I identify the transformations that are going on inside this function, apply those, and then hopefully once you get used to these, after you apply these 3 pieces, there's no question what the graph's going to look like. You might want to refer to, like, did we do a vertical reflection or horizontal reflection, just to remind yourself of what it should look like. But we have a great sketched version of the graph here. Last thing I want to say is about this shift right here and what our new domain is. So this function right here, I graphed it. You know the original function log of base 3 of x had a domain from, based on this vertical asymptote, of positive numbers. So a vertical asymptote at 0, so inputs were strictly positive. Well, this shift left right here, we can graphically see the domain here. The domain now is restricted by this vertical asymptote at negative 3/4. And importantly, the domain of this function is now negative 3/4, comma infinity. So we are allowed actually to plug in negative numbers, negative up to negative 3/4, not including negative 3/4. And now what I finally want to say is, if you didn't want to sketch this and define the domain of this function, all you'd have to do is take this expression 4x plus 3, and actually I'll do it just right here. So another way of finding the domain would be to take 4x plus 3 and set it greater than or equal to 0. And when you solve this, you're going to find that you're going to get the same result. This says, well, if you want that input to be greater than 0, then you're going to need to input values that are greater than negative 3/4, which was shown through our work of graphing this function. All right, in our second example here, we're being asked to sketch a graph of f of x equals 3 times the log base 1/3 of x minus 2. 3 different things going on here. We have this decreasing logarithmic function now, this decay logarithmic. We also have this multiplication of 3 out front. This is a vertical stretch by 3. So we're going to multiply our y values, or our outputs, by 3. And in this case right here, this minus 2 is a shift right 2 units. So to start things off, we just look at our base function here. Again, our base function that we're going to be looking at is the log base 1/3 of x, which will have all of these same attributes as before. It goes to the point of 1, 0. It'll go through the point of the base of 1/3, 1. And if we look at a graphical representation of this, we do expect this, again, because that base is 1/3, this is a decreasing logarithmic function, but we also, as always, have this vertical asymptote at x equals 0. First thing we're going to do is apply our stretches. So our vertical stretch in this case is a multiplication of 3 to the y values. It's actually only going to affect this point right here. So 1, 0, because 0 times 3 is still 0. This becomes 1/3, 3, and then our vertical asymptote stays exactly the same. Then what we're going to do is apply our shift, which is right 2 units. So we're going right 2 units. Which means we're adding 2 to our x values. This will affect our vertical asymptote. And so this becomes 3, 0. 2 plus 1/3 would be 7/3, which is also 2 1/3. When I'm graphing it, I usually will think of it as like 2 1/3, but I'll write it as 7/3 right now. The y values don't change. My vertical asymptote that was at 0 now is a vertical asymptote at x equals 2 when I do this shift to the right. All right, so let's plot these points and sketch this graph. And so again, just to remind ourselves when we're doing this, what happened? We had a vertical stretch, so we're 3 times bigger in terms of the y values, and we shifted right 2 units. One thing, I'm just going to do it differently here this time. I'm going to go starting with the vertical asymptote. This really helps me orient myself and make sure I don't do anything really kind of strange on both sides of the asymptote. I know I have a vertical asymptote at x equals 2, so I'm just going to throw that in here first so nothing wonky happens. And now I'm going to plot these 2 points. So I'm at 3, 0, which is this point right here. This got a little strange. Let's just move that over. So this is 3, 0. And then I also have the point that's 2/3, 3. So I'm at 2, 2/3 is somewhere right here, 2/3, 3. And actually I can see right away that that has that stretch going on there. That really takes this graph from looking like this, and now it's 3 times vertically bigger. I have my asymptote here. I didn't have a vertical flip, so I'm still coming from positive infinity. And actually, I can sketch that graph right now. So I'm coming down from positive infinity. It's a decay logarithm. Oh, this is going to be tight. I got to make this look good. Uh-oh, sorry about this. We're going for it. That is a sketch of this graph right here. I got kind of chubby here as I tried to make it look good, but you can get the idea right there. So again, I've applied these transformations. I had to visualize this idea of this logarithmic function. And again, knowing that that base is between 0 and 1 really helps you with the idea of what this is going to look like when it comes to sketching the transformation. Knowing that it's a decay model, know it's going to be decreasing along this interval. Unless I have a vertical flip, actually would change the nature of that. Last I want to talk about here is the same conversation I had previously. This function right here, logarithms strictly allow positive inputs, but in this case, since I have this transformation that's changed, my domain now is strictly values bigger than 2. So the domain of this function is from 2 to infinity, and that's because of that transformation, which is related to that subtraction of 2. And that should make a lot of sense. If we need to make sure this input is strictly positive, then we have to plug numbers bigger than 2 into this to set to when x minus 2 occurs, when that operation of subtraction of 2, to ensure that's still positive, I need to make sure my x value is bigger than 2.